Hey, today we're going to come up with the concept of the derivative as a function. Gonna be great. Let's start with the function f of x equals x squared. And why don't you take a moment and use what we've learned so far to compute f prime of 5 using our definition of the derivative at a point that I've just scrawled in the corner over there. F prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. So pause the video, take a moment or two, do this computation, and then we'll reconvene when you're ready. And you get that f prime of 5 is the limit as h approaches 0 of f of 5 plus h minus f of 5 all over h, which is the limit as h approaches 0 of 5 plus h all squared minus 5 squared all over h. And you do a little algebra. And you eventually get down to that it's the limit as h approaches 0 of 10 plus h, which is just equal to 10. And if there's any part of that that was confusing or that you don't understand, then make sure to go back through it and look at it carefully, because this is key and important and not that hard. And you're going to be asked to do it again and again. In particular, you're going to be asked to do it again right now. Same function. See if you can compute f prime of 7. So do the same thing, but instead of computing the derivative at 5, compute the derivative at 7. So really do it. Take a few minutes. Pause the video. When you're ready, start it back up again. And you do a bunch of work, and you find that the derivative at 7 is equal to 14. And that's not really the interesting part. The interesting part is basically how uninteresting that was. In particular, it's really the exact same calculation that you just did for 5, just with a different number. But the concepts, the maneuvers, the techniques that you used, all the same. Every single step analogous to the one that you did for the other number. No different tricks. Works out so that the algebra is basically all the same. It's just the particular number that differs. And the thing is, there's lots and lots and lots of numbers, and we might want to know the derivative of this function x squared at 11 or 26. Or negative 31, or pi. And, I could ask you to do each one of those, but still, there are lots and lots more numbers. And so what we really need is something better, some way to find the derivative of this function at any arbitrary number. Let's call it x. Then here's where the fun really begins, and I apologize for squeezing it into the edge here, but I didn't leave myself quite enough room, but we'll see if we can do it anyway. We've got that f prime of x, by the exact same way we figured out f prime of 5 and f prime of 7, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, where instead of the 5 or the 7, I'm using the x. No other difference. And f of x plus h is just x plus h squared, just like f of 7 plus h was 7 plus h squared. And f of x is x squared, just like f of 7 was 7 squared. And then you do the same algebra to get this limit here, where all I've done is expand x plus h squared into x squared plus 2xh plus h squared, which is what it is. Just like 7 plus h squared was 49 plus 14h, which is 2 times 7 times h plus h squared. And just like in the previous two examples, the x squared terms, which were 25s and 49s before, but are now just x squared, they cancel. And we're left once again with something that has an h in both terms in the numerator, so we can factor it out, like so. And after that, the h's cancel. And the limit as h approaches 0 of 2x plus h is just 2x. And what we've just said is that the derivative of the function x squared is the function 2x. And you can see that we found before, when x was 5, we got the derivative was 10, 2 times 5. And when x was 7, we got that the derivative was 14, 2 times 14. And so now we don't have to do it for every possible number. If we needed to know the derivative of this function x squared at the point where x was equal to 91, we'd get 2 times 91, or 182. And what we've just come up with is the concept of the derivative of a function. The derivative of a function f is the function f prime of x, which is the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that this limit actually exists. In other words, the exact same thing that we had for the derivative of the function at a point, but instead of picking the derivative at a point A, we now do it at a variable x, but it's the same definition, replace the a with an x. All of the following are notation for the derivative of a function y equals f of x. There is, of course, f prime of x, which we have already described, sometimes abbreviated as simply y prime. You'll see it written quite often as dy dx, and we'll talk more about that one in just a moment. Variations on that include df dx, and this little beauty, d dx of f of x, sort of. There are a few others, but these are the big ones, and so these are the ones that we'll focus on right now. If you recall that the derivative of a function at a point originated from looking at the limit of the slopes of secant lines, then it gives you a way to think of this dy dx as just the limit as the delta x part, the change in x part, goes to 0 of the slope of a secant line, change in y over change in x. So change in y over change in x, that's the slope of a secant line. And as that delta x part gets smaller and smaller and smaller, we approach this thing that we now call the derivative, and that's where the dy dx comes from. The delta is the Greek letter, essentially the Greek equivalent of the letter d, so that's where the d's come from. It's also worth mentioning that the process of taking the derivative, often called differentiating, so you see some problem on an exam and it says differentiate and it gives you some function. All it means is find the derivative. Okay, all that's left is to try some. Let's start with the function f of x equals x cubed. I'll get you started and then I'll let you finish it yourself. By definition, the derivative of any function is the limit as h approaches 0 of f of x plus h minus f of x all over h. I just got myself some partial credit, by the way, so you may as well write that. And in this particular case, f of x plus h is x plus h cubed, and f of x is x cubed. So now there's some algebra to do. And one way you can certainly do it is take x plus h and multiply it by itself 3 times. Or you can recall what you learned from the video on Pascal's triangle and use that to compute x plus h cubed. So whichever way you'd like to do it, I recommend the Pascal's triangle way because we'll see it again soon and it will be helpful if you'll have practiced it. But either way, take a few moments and see if you can compute the derivative of the function x cubed. See if you can finish this computation, pause the video, and when you're ready, start it back up. Turns out that x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed, whether you work that out carefully by hand or use Pascal's triangle. Beautiful things happen. You can see that the x cubeds cancel. And now we're in great shape because everything left in the numerator has an h in it. And so we can factor that h out, cancel it with the 1 in the denominator, to get the limit as h approaches 0 of 3x squared plus 3xh plus h squared. To compute that limit, all you have to do is plug in h equals 0, and when you do, you get the answer 3x squared. So if f of x is x cubed, then f prime of x is 3x squared. Just to very quickly show you how some of that other notation can be very useful, we could write this like this. This says the derivative of the function x cubed is 3x squared. And the beauty of that is we didn't have to make up a name for it. If you hadn't already called it f for some reason, and you were just looking at the function x cubed, well, there's no reason to name it just so that you can say f prime is equal to something or other, or y prime or something like that. Nope. It's just the x cubed part. Take its derivative. What do you get? 3x squared. Okay, you try this one. I'm not going to help at all. I mean, I'll do it for you when you're done, but do it. Just pause the video, stop, see if you can find the derivative of this function g. And then when you're ready, start it up, and I'll show you very quickly how it's done. So by definition, the derivative is the limit as h approaches 0 of g of x plus h minus g of x all over h. What is g of x plus h? Well, you plug x plus h into the function and you get 3 times x plus h minus 7. And then you have to subtract the function, and you have to be careful. You need the parentheses that I've put in over here, because otherwise you wouldn't be subtracting this entire function. And so that's very important, so don't forget those. You do a little algebra, you see that almost everything is going to cancel here. And you're left with the limit as h approaches 0 of 3h over h. The h's cancel, that's the limit as h approaches 0 of 3, which is of course 3. And you say to yourself, self, how did I get an answer that's just a number? And the answer is, the function we're talking about, 3x minus 7, is a straight line. It's a line with slope 3 and y-intercept negative 7. And what does the derivative tell you? It tells you the slope of a tangent line at any point to this curve. Well, take any point, pick one, say right over here. And what's the slope of a tangent line? Well, a tangent to the curve right there is precisely the curve itself. It's the same line. And so the tangent lines all have slope 3. And so that's why we got this constant, because any tangent to the line 3x minus 7 is the line 3x minus 7 and so has slope 3. Okay, one more for practice and then you should be all set for your homework. There's nothing different conceptually, but just like we did when we did the derivative at a point, this one requires, we looked at this function when we did the derivative at a point, and it requires a little bit of extra algebra, in particular combining fractions that have denominators that are not exactly the same. So take a few minutes and remind yourselves of how the algebra works, work your way through finding the derivative of this function, and then we will look at it together. I just snarfed up my partial credit. Why not? I got a point for writing that I understand what the definition of the derivative is. And then I applied it to this particular function. F of x plus h is 1 over x plus h, and f of x is 1 over x. And to combine those two fractions, you need a common denominator, and the common denominator is x times x plus h. And after you multiply the first term in the numerator by x over x, and the second term in the numerator by x plus h over x plus h, you get this expression here. Now both terms in the numerator have the same denominator, and so we can combine them. You have to be a little bit careful with subtracting the entire numerator of that second term, so you need those parentheses. And I've combined two steps here in the numerator, x minus the quantity x plus h. Well, x minus x is 0, and after you've distributed the negative sign, we're left with a negative h in the numerator. And then dividing that whole thing by h is the same thing as multiplying by 1 over h. And you probably didn't really need me to write this step in order to see that the h's are going to cancel, but I wrote it anyway, no extra charge. And we're left with the limit as h approaches 0 of negative 1 over x times x plus h. This is a rational function that is perfectly well defined at h equals 0, so we can just plug in h equals 0 to compute the limit. And we're left with the derivative of 1 over x is negative 1 over x squared. We're going to do this derivative, the derivative of 1 over x, at least 5 different ways over the course of the semester. It will always come out to be negative 1 over x squared, but we'll learn a lot of different techniques along the way. Okay, that was the derivative as a function. Hope you enjoyed it. You are in good shape to start your homework. You're in good shape to finish your homework. So take a stab at the homework, and I will look forward to seeing you soon. Bye.